This is section 5.7 on exponential modeling, and we'll be doing a little bit of logarithmic modeling as well. We've actually done some exponential modeling already, and we'll be reviewing some of that. But in addition, now that we know how to solve our exponential equations and our log equations, we can actually do more with our models than we were able to do before. So in example 1, we have a description here. Let's see, one of the most notable occurrences during the early part of this century was the expansion of the internet. In the year 2000, there were 17.1 million websites, and on average, the number of websites grew by about 33% per year. We are supposed to work by hand, first to find a modeling function, where t is years after 2000. So I'm thinking, well, let's see, this is a percent growth. Anytime I have a constant relative growth rate, I always use exponential functions, and it tells me exponential anyway. So I know I'm going to go for y equals ab to the t, basically. Now my a value is always the starting amount. And in this case, we knew that in our starting year, 2000, there were 17.1 million websites. So I'm thinking we can go with A as 17.1, assuming we're doing this in millions. And then for the B is what incorporates that relative rate of change. Right? We know that the websites grew by about 33% per year. 33% isn't exactly the B value, but it gives me what I need to get it. So remember that 33% is on top of the 100% that we had started with for a total of 133%. And if I change that to a decimal, my B value is 1.33. So I'm going to go with f of t, I guess I'll call it, is 17.1 for A times the 1.33 to the t power. All right, that hopefully looks at least somewhat familiar because we have done that before. And part B, again, should be something you're thinking, yeah, I feel like we've done this before. We just want to use our model here to predict how many websites there would be in the year 2018. So that would be 18 years after 2000. So t equals 18. And if I just plug 18 into the function that we just found, let's see, I get about 28.99. I'm going to call that 2,900. I'm going to run, well, actually, I guess they kept one decimal place. I can do the same. 2899.5. And that would be million websites. Notice that that's actually 2,899,000,000, so almost 3 billion. That's what we're looking at there. And the last part is the part that we were not until now able to do without technology. In what year does the model predict the websites first reached 1 billion? Well, let's see, I got to do this in millions. So that would be 1,000 million. So I'm going to go ahead and put 1,000 in for the f of t, the number of websites. And then I'm going to go ahead and solve that. All right, here's where we're going to use some of those new skills from the last section. To solve for t, the first thing I need to do is isolate my exponential. So I'm going to divide by the 17.1. And let's see, I've got about, what is that, 58.5 roughly. I'm going to keep the whole number in my calculator, so I'm just going to write that as 58.5. And then I need to get to the t, so I need to get rid of the exponential, base 1.33. The inverse function for that would be the log, base 1.33. And I'm going to do that on both sides. All right. So let's see. I go to my log base, or you can do this on Desmos, of course, but I got my calculator handy today. I'm going to my log base, and I want the log base 1.33 of 58.5. And you know what? Actually, I said I was going to do something, and I didn't do it. Instead of rounding that to 58.5, I was going to go back up and use that whole number that I had. I'm going to redo it. Keeps more accuracy. So log base 1.33, and I'm going to go up there and grab that whole number in all its glory. And it's the same for the first couple of decimal places, but you'll notice there is a slight difference by the time I get to the third decimal place. So I'm going to call that 14.267. And those, goodness, I'm so sorry. When I copied here, I copied badly. That was 1.33, not 58.5. There we go. So I just brought that 1.33 to the t down, and then we took the log base 1.33 on both sides. On the left side, even using the more exact value, I did get the 14.267. And then on the right side, these are inverse functions. So I'm just going to get t. So let's see, that would be during 2014. We first reached 1 billion websites. All right, let's try another example here. You may remember our doubling and half-life type problems. This is one of those, so we'll get a chance to review the setup of that, and then again to apply some of our newer skills. So we have a nuclear disaster. Probably remember this occurred in Ukraine, in Chernobyl, 1986, and a lot of radioactive materials were released into the environment. One of the most dangerous was cesium-137, which has a half-life of 30 years. So we're supposed to work by hand, first of all, to come up with our exponential model, C of t equals AB to the t. And the model is for the percent of cesium-137 that remains t years after the nuclear meltdown in 1986. So let's make ourselves a little table of values. I almost always do this with half-life and doubling types of problems. At time 0, 1986, when the accident occurred, all of the cesium-137 that was ever going to be released was released right then. So the percent would be 100. Now with a half-life of 30 years, 30 years later we're down to 50%, right? Cuts it in half. And let's just do a couple more for practice. Another half-life, so 30 more years would bring us to 60. And that would be cut in half again, down to 25%. And let's go one more half-life. 30 more years brings us to 90. And again, that would be cut in half again, 12.5. You could keep on going as long as you wanted to for that, but that's actually more than enough. All right, so we're going with C equals AB to the T. And I do know A. I know the starting amount, or y-intercept, is at 100. So that's going to be my A value, is 100. All right, these do not go up by ones, so I can't pick the B value out of the table. Instead, I'm going to take one of my other points and substitute it in. So let's go ahead and take this one. Plug that into my equation. So C is 50 and T is 30. All right, I'd like to solve that for B. So I'll begin by dividing by 100. Gives me 1/2, or 0.5, equals B to the 30th power. And to get rid of the 30th power, I use the reciprocal, the 1/30th power. And of course I have to do that on both sides. All right, they said to use 3 decimal places, so let's get that value correct to 3 decimal places. .977 for the B. So I'm going to say that my model looks like C of T equals, A was 100, and we just calculated B as 0.977 to the T power. And again, can't emphasize enough, I personally think making at least a little table of values, even a couple points is fine, but at least making a little table of values for these half-life and doubling and tripling kinds of problems is really the way to go. Then you got something to work with. All right, our base was 0.977. And I want to interpret that as the relative rate of change. So that'd be 97.7%. Now I have to take back out the 100% that I started with. And that leaves me with negative 2.3%. So the amount of cesium-137 is decreasing by 2.3% per year. All right, again, both of those are things that you could have answered earlier in this unit. But here's the one that we need our more recent skills for. How long is it going to take the amount of this radioactive cesium-137 to be reduced to just 10% of the amount that was originally released in the disaster? During what year is this going to occur? All right, so if I want 10%, I want C equal 10. By the way, one of the most common questions that I get here is, should I use 10 or should I change it to a decimal and use 0.10? It all depends on how you started, right? In my case, my percents of cesium were actually given as 100%, 50%, 25%, not 0.25 and 0.50, and so on. So I just have to be consistent. Since I use the whole number percents here, not the decimals, I'll do the same down here. So I am going to go ahead and use C equals 10. So I'm going to plug that in for C. 10 equals 100 times 0.977 to the t power. All right, let's solve that equation. To isolate the exponential, I will divide by 100. So 1/10 or 0.1 equals 0.977 to the t power. To get to t, I need to get rid of the exponential, 0.977, and the inverse function for that would be a log, base 0.977. So I'm going to apply that log to both sides. All right, on the left-hand side, let's see what we get here. In my math menu, go down from my log base. I want the log base 0.977 of 0.1. That's about 98.96. On this side, I've got those inverse functions, so that's equal to t. So it's going to take 98.96 years, and that's the first part of the problem, is how long will it take? And then the second question was, during what year will this occur? Well, remember, we started in 1986. So if we add that t value, what would we get? Let's see, we get the year 2084. Technically 0.96 or whatever, but it's the very tail end, but we're still during the year 2084. And notice this answer really does make sense, that 98.96, because notice at 90 years, we were down to 12.5%. So it takes just a little longer to get down to 10% than that. So pretty confident with that answer. All right. So far, whenever we've done an exponential model, we've always used the y equals a times b to the t. Right? We actually could choose, if we wanted to make our exponential models have a base of e. And in fact, every exponential model could be written base c if we wanted to. In that case, we're going to use a slightly different form. We're going to say y is equal to a, e to the kt. We're going to go ahead and explore that just a little bit, and we'll use some does most defined functions of this form as well. And then we're going to go ahead and get models in that new form for our two examples that we've already done, and then just kind of compare and contrast. So the problem that we just did was example 2. That was our radioactive cesium-137. We got 100 times 0.977 to the t. The problem that we did before that was the internet, the websites, and we got f of t there was 17.1 times 1.33 to the t. Relative rate of change here, they gave us, it was 33%. And the relative rate of change here we calculated, it was 2.3, technically negative 2.3%. So that's just a summary of what we already did in examples 1 and 2. I would now like to redo those examples and get an exponential model in the base E format. So I'm going to do this with a table in Desmos. And basically, I'm going to base my regression equation on that equation right there. So I'm going to go back. I'm going to do the cesium 137 one first. And I'm going to make a table. And I'm going to go ahead and put in those values that we already did. This is just from example 2. All right. We had calculated this by hand, but I'm just going to remind you that if I do my usual AB to the T, oops, I guess it's got to be X1 here. There's that A is 100, and there's that B equals 0.977, exactly what we had calculated by hand. Let's see what happens if I change the model. What if I do AE to the K, we want T, but of course Desmos wants X1. Notice it gives me my parameters here. A is still 100, same as it was before. But here's that K value. It's about negative 0.023. So if I wanted to write down the model here, this was example 2, A was still 100, and that was times e to the negative 0.023 t. So instead of doing a base in that form, I'm using the base of e. What I want you to particularly notice here is how that rate of change happens. We know how to calculate it from here, right? We just turned it into 97.7% and subtracted the 100%. But notice in the E form, it's actually right up there in the K value, right? If you changed negative 0.023 to a percent, you would get negative 2.3. So one advantage of using a base of E is our relative rate of change is actually easier to see. It's really obvious. Let's go back to example 1 for a moment and see if we can calculate that one. We were given the 33% as our rate of change on that one. And if I wanted to get an exponential model base E, I'm going to need some data that I can plug into Desmos. So let's come back here for just a moment. We didn't make a table for this, but it wouldn't be very hard to get at least a couple of points. We know we did start with 17.1. And if I just go ahead and calculate 1 year's worth, started with 17.1, multiply that by 1.33, right? Keep 100%, add 33% more, and that's 22.74. All right, 2 points are actually enough to get an exponential function, so I'm going to use that little table. I'm going to come over here and put that in Desmos. And let's get the E form this time. AE to the KX1. You see the A is still 17.1, and you see the K value there, 0.285 rather. So if I want to write down my exponential form, I have the 17.1, the starting value is exactly the same. And then I have e to the 0.285 t. So looking at that, I'm thinking, well, gosh, this one worked out so well, right? The K value up here just gave me the relative rate of change. In this case, it was a bit different, and it's actually because this is a much larger rate of change. What's happening here is the difference between an annualized rate of change and a continuous rate of change. This 33% that I got here basically says at the end of every year, we had 33%. This 0.285, or as a percent, 28.5%, is what we call a continuous rate of change. It's kind of like the same idea as, do you wait till the end of the year to put all your interest into the account, or do you put it in a little bit at a time, right? Or does the bank put it in a little bit at a time? This is what happens if you wait till the end. This is what happens if you put in a little bit at a time, so that the rate of change builds on itself, the same way as interest builds on itself when we have that continuously compounded interest. Again, you'll rarely see much difference when the K values are very small, but for larger K values, you often do see that difference. So, annualized per year, continuous rate of change down here. You'll talk a bit more about that in other classes if you go on and take more math, but just a little bit of a preview of coming attractions there. All right, let's make that a bit formal by talking a little bit down here. We already know the relationship between the relative rate of change and the base B from the exponential model f of x equals ab to the x. Here we take our b, we change it to a percent, and we subtract 100% to get the relative rate of change. But that is per whatever your time units are, per year, per hour, per week, whatever your units of time are. I'm just going to say per year here, but know that that would work for any unit of time. If I write my exponential function in the form ae to the kt, then with the k, all I'd have to do is change it to a percent. Don't have to add or subtract the 100% at all. That's taken care of by the process. And this gives me the continuous relative rate of change. These are very similar in the case of relatively small b values. They show up as somewhat more different as the b value gets a little bit larger. And this is always going to give you a larger rate of change than this one, because this one you don't have to grow as fast if you're growing continuously as you do if you wait till the end of the year to apply the changes. All right, and it talks at the bottom of the page a little bit about how you'll talk more about this in future math classes. So let's see here. In example 3, modern manufacturing techniques rely heavily on the use of industrial robots. The chart here shows us the number of robots in industrial use for various years. We're going to go back to our R of t equals ab to the t to find a model for this data in the year that is t years after 2010. So my t equals 0 is the 2010, and then I'd have 2, 4, 6, 8, and 10. All right, let's put that in there. It says to use an exponential function, but we haven't done this yet today. Let's verify that it looks exponential as well. All right, so my data goes in. And I'm going to go ahead and do the zoom fit. And you can see that there's more of a curve to this than I would expect if it were just linear. So this does look like part of an exponential growth curve to me. So we wanted the AB to the teach form this time. Oops, got to use X here though. And visually I can see it's a pretty good fit. R squared is 0.99, that's a great fit. And there are the A and the B values. So I'm going to write this as, let's see, this is robots, so they wanted us to use R of T. And let's see, I should be able to get my screen share in here. So that would be 0.977 for A times 1.119 if I round to 3 decimal places. For the B, raised to the T power. My base is the 1.119, and I'm going to change that to a percent, 111.9%. Subtract off the 100% we started with to find out how much it changed, and that rate of change is 11.9%. Now this is technically an annualized rate of change, since we use the AB to the T form. So we could say that the number of robots or number of industrial robots increases, this is a positive rate of change, by 11.9% per year. All right, it then says use the model to predict the year during which we would have 6 million industrial robots. The number was in millions, so I'm just going to put 6 in for R. And let's see, if I do this by hand, it says by hand verify with technology, I'd be dividing by 0.977. About 6.14. And then I need to get the t by itself. To do that, I have to get rid of an exponential. Base 1.119. The inverse would be a log. Base 1.119. All right, so I need to do that log, which I'm just going to do on my calculator here. It's about 16.14. And on the right-hand side, I've got those inverse functions going on, so I've just already solved for t. So let's see, this would be during the year 2026, right? We started in 2010, so during 2026. All right, let's verify this one. We've already got our graph on Desmos anyway. Let's verify it there. I wanted to know when y was 6. And I can't see that right now because I don't have a large enough graph, so let's fix that. There we go. Oops. And notice I get a slightly different value, 16.15 this time, or 16. That's just because I rounded off my numbers and they're using all of the decimal places. But notice it would still be the year 2026, the way they did it as well. All right, in our next example, with the rise of online shopping, more and more money is being spent on purchases from companies that have no brick and mortar physical shopping space. The table below shows how much is spent at only online businesses from 1992 up to, in a variety of years, 2018. And you can see this is in billions, the amount spent at these online-only businesses. So we are supposed to, once again, or excuse me, this time we want to use the AE to the KT form. And we would like to do this in amount spent T years after 1990. So my T would be 2, 6, 10, and so on. Go. And we'll go ahead and put both of these into Desmos. And let's just take a look at that data. There we go. Looks like an exponential growth function to me, so it can certainly seems reasonable that we would be using an exponential model. Now this time they specifically wanted us to use the AE to the KT form. And by the way, on homework or on a test or whatever, I would need to tell you which one I want. They're both valid models, and so I would need to tell you which one I was expecting. All right, so in this case, we're going to do the Y1, and we wanted the AE to the K X1. Again, visually, I can see that my model is very close to all the points. R squared about 0.98, really close to 1, so things are looking good there. And there's the A and the K. So if I want to write down this model for M of T, A was 5.591. And then I have E raised to the, K is 0.0825 times T. And actually, I probably should have used a slightly different word here. What is the continuous? Because this always gives us the continuous relative rate of change. Sorry about that. In the amount spent based on our model. Well, for that, we're going to look at the K value, 0.0825. And if I just change that into a decimal, into a percent, that would be 8.25% is the continuous rate of change. All right, and finally we want to predict when spending at online-only businesses will reach $100 billion. So we want to put 100 in for our M value. And they want us to solve by hand again, but then we can verify with technology. So I got to isolate my exponential, divide by 5.591, and that's about 17.89. Let's see, I need to get to the t, so I got to get rid of the exponential base e. The inverse of exponential base e is the natural logarithm. So let's do the natural logarithm on both sides. Natural log, and I'm going to go ahead and grab that whole number, is about 2.884. Natural log and exponential base e are inverses, so that's 0.0825t. And then I have to divide by the 0.0825 to get t. So I'm going to take my previous answer and divide it by 0.0825. I get about 34.96. So let's see. We started in 1990, so this is the very end of 2024. If we wanted to just check that out with technology as well, we could come back over here, and I'm going to get rid of all the points here and just add the y equals 100 line, since we're predicting $100 billion spent. And there it is. There's that 34.95. Very close to what we got by hand. Again, they've used a few extra decimal places. All right, those have all been exponential models. I want to just say one word about logarithmic models. In this class, we will typically use logarithmic models for very specific situations that rely on them. It's not that you can't do modeling, like using the regression stuff with them, but with all the choices of base as well as everything else, we'll typically just go ahead and use it for known situations that follow a logarithmic model. All right. Sometimes we can hear about the pH of a substance. Essentially, it measures the acidity. We measure the pH of a garden soil, pool water, various other things. And the way that scientists actually calculate pH is they experimentally measure the concentration of hydrogen ions in whatever it is they're working with. That concentration of hydrogen ions, notation there is that little H+. And then they calculate the pH, P of H+, as minus the common log of the H+ value. Okay. That's actually where pH comes from. P is a function of H+, but it's typically just shortened to pH in real life. All right, so let's see. Normal human blood has a hydrogen ion concentration of 4 times 10 to the negative 8th moles per liter. So notice that we just were given H+ here. Find the pH of human blood. So using our formula, the pH is going to be minus the log of that value which you can do either with Desmos or a calculator, negative log 4 times 10 to the negative 8th power is about 7.4. Okay, so normal healthy human blood, pH of about 7.4. By the way, sometimes science teachers ask me, hey, would you show them this too? So I just want to show you an alternative way to enter this in the calculator. If I take negative log, put in my 4, when you're using the base of 10, there's like a little shortcut button on the calculator. It's this double E. It's right above the comma key right here. And so I could do double E -8. And notice it gives me the exact same thing. Essentially, that double E key kind of puts in the 10 raised to the power for you. So if you're ever told, hey, just use that key, that's what it's for. I personally think it's just as easy to do this because then I don't have to remember something else, but that's up to you guys. All right, part B of this problem. A substance with a pH of less than 7 is an acid, and the lower the pH, the stronger the acid. A substance with a pH of more than 7 is a base. The larger the pH, the stronger the base. So is human blood an acid or a base? Well, notice with a pH of 7.4, it's actually more than 7, just slightly. So we'd say human blood is just ever so slightly basic, not acidic. So it'd be a very weak base. It's not much more than 7, so it's not a strong base. Carrying on with that theme, a very ill patient's blood is tested and found that their hydrogen ion concentration was 1.2 times 10 to the -7th. The patient is diagnosed with a disease called acidosis. Does the name of that disease make sense to you? Well, let's start by calculating the pH for this person's blood. It would be minus the log of 1.2 times 10 to the -7th. And it's about 6.9. Now that might not seem like much of a difference in pH from normal human blood, but it was enough to change it from a weak base to a weak acid, because 7 is the neutral point. And it turns out the human body does not tolerate having even slightly acidic blood, so this can make somebody actually very sick. So blood is now slightly acidic. And that's actually where the name of the disease, acidosis, comes from. So it kind of makes sense. All right, we've got one more problem to look through here in this section. Another situation where we use a logarithmic equation to measure something. You're often told about loudness of sounds in decibels, right? So a sound with intensity, X watts per square meter, which is something that's measurable scientifically, has loudness defined as 10 times the log of X over I naught, where I naught is actually 10 to the -12th, and that's the least intense sound that most people could hear. All right, we are supposed to first of all find the loudness of normal conversation, which has an intensity of 10 to the -6th watts per square meter. So the intensity is our X, so notice here we were just given the X value. And I'm just going to plug that into my loudness equation. 10 times the log of our X value, 10 to the -6th, divided by I naught, which is 10 to the -12th. Now, it's not that there's anything wrong with doing this in the calculator, but I think we actually, just for a little practice, I think we can do this one by hand. All those base 10s running around.
To divide, I'm going to subtract the exponents. So negative 6 minus a negative, or in other words, plus 12, would be 10 to the 6th. And notice I have a log base 10 and an exponential base 10. Those are inverse functions. So I end up with 10 times 6, or 60 decibels, for the loudness of normal conversation. All right, part B here. We're going to find another loudness. Amplified rock music. Intensity here is 10 to the negative first watts per square meter. So once again, I want to find L of x, the loudness, and I'm going to use my formula. 10 times the log of my x value, 10 to the negative first, divided by I naught, 10 to the negative 12th. And once again, just for a little practice, let's do this by hand. Not that the calculator wouldn't do it, of course, just as well. So that would be 10 times the log of, subtracting these exponents, negative 1 minus a negative 12 is negative 1 plus 12, so 10 to the 11th power. Inverse functions again. Gives me 10 times 11, or 110 decibels. By the way, I would not expect you to memorize these kinds of equations by any means. I would give them to you if you needed them. All right, I want to talk a little bit about those two answers. It actually doesn't really seem as though there's all that big a difference in the loudness, even though this is just sort of a normal conversation, and this would be like a super loud concert hall. So what's going on here? What's happening is a logarithmic scale, or a logarithmic equation, actually often hides the differences between things. To see how that works, let's go ahead and answer the two questions right here at the bottom of the page. Amplified rock music is how many times louder than normal conversation? Well, let's see. The loudness of the rock was 110 decibels. And I want to know that's how many times as loud as the 60 decibel. I'm going to call my multiplier here K. And so if I just divide both sides by 60, it's about 1.83. So the music is about 1.83 times as loud as the conversation. And I'm putting that loud in parentheses because I'm going to come back to that in just a minute. All right. Another question is, amplified music here is how many times more intense than normal conversation? Well, let's see. The music intensity was 10 to the negative first. And let's see, normal conversation, the intensity was 10 to the negative sixth. And I'm going to make my multiplier here, K. So if I divide both sides by 10 to the negative sixth, let's see, subtracting exponents, that gives me 10 to the fifth power. 10 to the fifth power is a 1 with 5 zeros. So the music is 100,000 times as intense. As the conversation. In everyday life, We use loud, the word loud, differently than scientists use it. When we say loud, we probably really mean intense because we experience that amplified music as much, much louder than a conversational tone. But what we're really experiencing is the very high intensity of the sound of the music compared to the relatively lower intensity of the conversation. So my main point here is when you know something has been calculated on a logarithmic scale, using a logarithm in the definition or the formula, keep in mind that it kind of masks the true relationship between things. Things are much, much, much more far apart than they may seem just by looking at, in this case, the loudness. All right, that brings us to the end of 5.7.